This video is about gravitational field strength and potential gradient. We'll begin with 2 points in a gravitational field that are at a short distance apart. We'll denote this distance as delta r. Let's also assume that the gravitational potential difference between the points is delta Vg. If you move an object of mass m between the points, work is done on the object, and this work, that we'll denote as W, can be expressed in 2 different ways. It is equal to either the mass of the object multiplied by the gravitational potential difference between the 2 points, or using the concept that work done by a force is equal to the magnitude of the force multiplied by the distance over which the object is moved, we get that this work done is equal to the gravitational force multiplied by the distance between the points. Since force is equal to mass times acceleration, we can rewrite our second expression for work as m times g, where g is the gravitational acceleration, times delta r. Next we'll equate these 2 expressions, giving us m times delta Vg equals to m times g times delta r. Finally, after simplifying by m and rearranging, we get that g is equal to delta Vg divided by delta r. Here is the related formula that is provided in the data booklet, along with the variables. There is a negative sign in this formula to indicate that as gravitational potential increases, gravitational field strength decreases. If you think about it, this does make sense, because as you are moving away from a uniform sphere, so for example from a planet, the gravitational field strength due to the planet decreases, while gravitational potential increases because we are moving towards infinity, where gravitational potential is 0. Finally, let's see the graphical interpretation of this formula, for which we'll use a gravitational potential versus distance graph, similar to one that we saw in an earlier video. The key here is that since on the vertical axis we have Vg, and on the horizontal axis we have r, the change in potential divided by the change in distance, so delta Vg over delta r, represents the gradient of the curve at any given point, hence delta Vg over delta r is called potential gradient. Therefore the gravitational field strength is equal to the negative of the potential gradient. On the graph, this means that if we want to find the gravitational field strength, for example at this point in the field, we can simply draw the tangent at this point and find the gradient of this tangent. Based on what we discussed earlier, the gravitational field strength at this point is the negative of this gradient. This completes our learning about gravitational field strength and potential gradient.